sometimes instead of giving probabilities, certain things will be given in odds. In particular, sports, newspapers, magazines, and websites often will refer to betting odds, and they'll be in the form Y to Z. So how does that relate to this idea of probability? Well, that means if you make a bet of Z dollars, then that bet will pay you Y dollars if your team wins, or your horse, or your whatever you're betting on. So if it's a fair bet, you should expect in the long run that you'll break even, winning about as much money as you lose. In particular, if you were to bet Y plus Z times, on average you should win Y dollars Z times and lose Z dollars the other Y times. So on average, if you bet Y plus Z times, you should win Z of those. I know that's kind of a weird way of thinking about it, but with odds, you ultimately should come out about even. However, if the person managing the odds wants to try to win or try to earn a little money, then maybe it won't always come out in this fair way. But if we want to relate odds to probabilities, you can think of your probability as being Z divided by that sum Y plus Z. So all you have to do to go from odds to probabilities is to use this formula. So we can look, the New England Patriots had odds of winning the Super Bowl 53-1. So how would we express that as a probability? Well, that means at 1 out of 3 plus 1 times they would win, so it's a probability of 1 out of 4. Now for a comparison, that same year, the San Francisco's odds were 6,000-1, so they had a 1 out of 6,000 plus 1, or 1 out of 6,000 probability of winning. We can also think about probability models for sampling. So choosing a random sample from a population and calculating a statistic, like the sample proportion or the sample mean, is going to be a random phenomenon. We don't know what is going to happen when we take that sample. However, we are going to be looking at the distribution of that statistic, and that's going to tell us what values it should take and can take, and how often it will take those values. And that's what we're going to be working on in part 4 more specifically, but we're going to take a look at it now to help us start thinking about what's to come. So let's take a simple random sample of 1,015 adults, and then we're going to ask them whether they feel childhood vaccinations are extremely important. So we can find the proportion who say yes here by counting how many of those 1,015 people say yes. Let's say, for example, we did 1,000 samples just like this. We would expect a distribution to come out looking relatively normal. So this histogram is representing 1,000 different samples, and we have plotted the value of the sample proportion. How many said yes out of that sample? And the center of this distribution should be around the true population proportion. And so we should expect about 54% of Americans would find vaccines to be extremely important based on what we see in these samples. So we've got this repetition happening, this regular pattern, and that's ultimately one of the big ideas of statistics. What we form the foundation of how we can use statistical methods in the last section of this course in order to take samples to explain what's going on in the population. And often the normal distribution is going to be a helpful way for us to understand what's going on in these probability distributions. Now, the normal curve is ultimately this idealized version of what would happen if we could take lots and lots and lots of simple random samples. Pretty much what would happen if we did this forever. Because think about probability. That's the pattern we see in the long run, and that would explain why we should be thinking of this normal curve as coming from an infinite number of samples. So our normal curve is what we're going to be using to assign probabilities to these sample proportions computed from random samples. So let's connect a little bit here. We are going to assume that we're looking at this normal curve from these samples with a mean of 0.54 and a standard deviation of 0.016. So remember back in chapter 13, where we had that 68, 95, 99.7 rule. Well, that told us that 95% of all of our data was going to fall within 2 standard deviations of the mean. Well, we can apply that here to our samples, and that means that 95% of our samples will fall within 2 standard deviations of the mean. So 2 standard deviations would be 2 times 0.016, which gives us 0.032. So take that 0.54, subtract 0.032, and add 0.032, and we know that 95% of our sample proportions are going to fall between 0.508 and 0.572. So now we have this concise language for the fact of what we would expect to see in the population. The probability is 0.95, that between 50.8 and 57.2% of the people in a sample will say yes when given that question. So this word probability is saying that what we're talking about would happen in the long run in very, very many samples. So even when we did that 1,000 simple random samples, that still wasn't very, very, very many. Now, it did give us something very close to what we would have in that infinite example. Here, from our 1,000 samples, we did see that 95% were between 0.509 and 0.575, which was awfully close to what our idealized version said. So 1,000 samples gets us really close. And that should help you see that it really is okay for us to use the normal curve for approximating what's happening in this histogram where we're looking at all of the different samples. And there's a special name for that histogram. It's called the sampling distribution of a statistic. And what it does is it tells us the values that the statistic takes in repeated samples from the same population and how often it takes those values. So you can think about the sampling distribution as assigning probabilities to the values the statistic can take. And we often will describe that normal curve that we lay over it as a density curve.